What if I told you that you've already seen this video? What if this isn't the first time you've heard this, and you're actually stuck in a time loop, reliving these exact moments over and over again? It sounds like science fiction, but some very real scientists have tried to make it a reality. Welcome to the Bizarre Bureau, where today we're diving headfirst into the mind-bending world of time loop experiments and the audacious researchers who tried to break the fundamental laws of causality. So, what exactly is causality? It's the simple, elegant principle that every effect has a cause, and that cause must happen before the effect. I drop a glass, it shatters. The drop is the cause. The shatter is the effect. Simple, right? But what if you could send a message back in time to tell your past self not to drop the glass? This is the grandfather paradox in a nutshell, and it's the kind of temporal headache that has kept physicists awake at night for decades. If you prevent the cause, how could the effect ever happen? And if the effect never happens, what prompted you to send the message back in time in the first place? It's a loop, a closed time-like curve, where the future influences the past, which in turn creates the future. This isn't just a thought experiment for philosophers. Some of the most brilliant minds in physics have seriously grappled with this. It all starts with Einstein's theory of general relativity. His equations, which beautifully describe gravity as the curvature of space-time, have some peculiar solutions. One of them, discovered by the mathematician Kurt Gödel, described a rotating universe. In this bizarre cosmos, if you travel far enough in a specific direction, you could actually arrive back at your starting point before you even left. You could literally shake hands with your younger self. While our universe doesn't seem to be rotating like Gödel's model, his work opened a theoretical door. Relativity itself doesn't strictly forbid time travel to the past. This brings us to the concept of wormholes, or Einstein-Rosen bridges. Think of space-time as a giant sheet of paper. To get from point A to point B, you'd normally travel across the surface. But what if you could fold the paper and punch a hole through it, creating a shortcut? That's a wormhole. Physicist Kip Thorne, a Nobel laureate, proposed that if you could create a stable wormhole and accelerate one of its mouths to near the speed of light, and then bring it back, you create a time difference between the two ends. Step through one way, you travel forward in time. Step through the other, and you're in the past. The catch? We have no idea how to create or stabilize a wormhole. It would likely require something called exotic matter with negative energy density stuff that, as far as we know, doesn't exist in the quantities needed. But that didn't stop scientists from trying to test the paradoxes, even without a full-blown time machine. One of the most fascinating experiments was conducted by physicist Raymond Jiao at UC Berkeley. He didn't use wormholes, but something much smaller, photons, the particles of light. In a quantum mechanical phenomenon known as quantum tunneling, a particle can pass through a barrier that it classically shouldn't have enough energy to overcome. It's like throwing a tennis ball at a wall and having it appear on the other side. Jiao's experiment in the 1990s showed that photons tunneling through a specific barrier appeared to arrive at the detector faster than photons traveling the same distance through a vacuum. It was as if they had traveled faster than the speed of light. Now, this is where it gets truly weird. The result was so mind-boggling, it suggested that the effect of photon arriving was happening before the cause was complete. This is called the Hartman effect. So, did Jiao break causality? Not quite. The problem is that you can't use this effect to send a meaningful message. The peak of the photon's wave packet might arrive faster, but the information itself, which is encoded in the front of the wave, never exceeds light speed. It's a subtle but crucial distinction. Causality lived to see another day, but the experiment showed just how bizarre the rules can be at the quantum level. Inspired by these quantum shenanigans, other scientists decided to tackle the grandfather paradox head-on using simulations and clever experiments. In 2014, a team of physicists at the University of Queensland in Australia simulated time-traveling photons. They used a special setup where one photon played the role of a particle traveling back in time, and another played the role of its younger self. Their experiment was designed to test a model proposed by physicist David Deutsch, a pioneer in quantum computing. Deutsch argued that in the quantum realm, paradoxes might resolve themselves. If you went back to stop your grandfather, the universe wouldn't break. Instead, quantum mechanics would subtly shift the probabilities to ensure a self-consistent outcome. You might find your aim is off, the gun misfires, or you simply change your mind. The Australian team's results supported Deutsch's idea. Their simulated time-traveling photon interacted with its past self, but the outcomes always avoided paradox. It seemed that at the quantum scale, nature has a built-in self-correction mechanism. Instead of a single timeline that can be broken, there might be a vast web of parallel timelines. When you go back, you're not changing your own past. You're just shifting to a different branch of reality, a different universe where things play out differently. This is the many worlds interpretation of quantum mechanics. It solves the grandfather paradox neatly, but at the cost of imagining an infinite number of parallel universes branching off with every quantum event. Another brilliant idea to protect causality is Stephen Hawking's chronology protection conjecture. Hawking found the idea of time travel paradoxes deeply unsettling. He proposed that the laws of physics themselves conspire to prevent time travel on a macroscopic scale. Even if you could build a time machine, the moment you tried to activate it, a massive feedback loop of virtual particles and radiation would surge through the wormhole, destroying it in an instant. It's as if the universe has a security system designed to prevent anyone from messing with its timeline. The universe, in Hawking's view, protects its own history. So, has anyone ever tried to find actual time travelers? You bet. Several researchers have set up experiments to look for evidence. One of the simplest and most elegant was conducted by two students at MIT who organized a time traveler convention. They widely advertised the event, but with a twist. They only published the exact time and location after the event had already happened. The logic was simple. If time travel is possible in the future, someone could read about the convention, hop in their time machine, and show up. They held the party, but alas, no one from the future RSVP'd. Other projects, like the Time Traveling Invitation Project, have left messages scattered across the internet and physical locations, containing specific keywords for future time travelers to search for. So far, the future has remained silent. Of course, this doesn't prove that time travel is impossible. Maybe future time travelers have a temporal prime directive, forbidding them from interfering with the past. Or maybe they're just not interested in our primitive parties. Or perhaps time travel is only possible to the point after which the time machine was created, meaning we can't visit the dinosaurs, but someone from 2050 could visit us now if we had a receiver. What these experiments reveal is something profound about our universe. They show that causality is incredibly robust. From the macroscopic world of general relativity to the weird probabilistic realm of quantum mechanics, the arrow of time seems to fly in only one direction. While physicists have found theoretical loopholes and pushed the boundaries in lab settings, they've never managed to send a single bit of information backward in time to create a genuine paradox. The time loop, for now, remains confined to our stories, our movies, and our imaginations. The scientists who dared to challenge it didn't break reality, but they gave us a much deeper, stranger, and more fascinating picture of what reality even is. They showed us that the fabric of space-time is more resilient and more bizarre than we could have ever imagined. Thank you for joining us at the Bizarre Bureau. What do you think? Is time travel possible, or is the universe's history safely locked away? Let us know in the comments below. And if you enjoyed this journey through space-time, don't forget to subscribe, and hit that notification bell so you don't miss our next exploration into the strange and unknown. See you next time. Stay curious.